networks, L networks, pi networks, T networks, and the components which constitute such networks between the source impedance and the load, they're all LC elements, lumped circuit elements, and we have assumed them to be lossless. Okay, so for example, there is no dielectric loss and capacitor, and we have not assumed any finite conductivity of the metal wires in an inductor. So, for example, if you have, for example, a source resistance Rs, and then you have the generator, okay, Vs. It has the source resistance Rs in series, and this has to be matched with with a certain load RL. Okay, you can decide on whether to go for you can have a choice. I mean, the matching network could be anything. It could be a two-component LC L network, and so this match network could be T network, pi network, anything. But so far, what we have assumed is that the components in the matching network are ideal. Okay, so we have considered a network made of ideal inductors and capacitors. So we have not talked about their efficiency of such networks. It turns out that due to the finite conductivity of metals, even radiation or even the dielectric filling between the capacitor, there is certain loss associated with such components which are constituting the matching network. So real components, however, are lossy due to finite conductivity of metals, lossy dielectrics or magnetic materials, and even radiation. So it turns out that due to such losses, there happens to be damping. Okay, by damping, I means there's a loss of energy, just like in a second order oscillatory system. Uh, you have a you have damping due to the it could be friction, it could be I mean any phenomena that is hindering the oscillations, and energy of the system is being dissipated in that way. So the quality is being reduced by damping phenomena. Okay, so the same thing is happening. For example, an inductor could be lossy. You can model an inductor. For example, if you are considering the finite resistivity of wire, I mean, in practice, you can model this with a small series resistance, RS, let's say. So instead of having an ideal inductor, a practical inductor will have some series resistance, okay? And that brings out a definition of the component quality factor. And that component quality factor, if we denote this by, let's say, U, then this is defined as the ratio of the reactor, XL, the reactance, divided by, since this is series, so this has to be divided by RS, okay? Because this series resistance is dissipative, and it's going to dampen the stored energy which is in the magnetic field of an inductor. Okay, so that's going to dissipate energy, and this dissipative energy is not going to reach the load. So you have to consider that. I mean, the same scenario happens. For example, you can have the loss in a capacitor, let's say. Okay, and for that case, if you're going to model this again with a certain resistance Rs, let's say we have a lossy capacitor. Loss in a capacitor is not large. I mean, it's dielectric, due to the dielectric filling. The loss is not comparable to what we have in the inductor. So, I mean, but if you're going to consider the component quality factor, it's the same. So, it's again, the definition is again XC. It's the reactance of the reactive element, which is in this case is the capacitor, divided by Rs. Okay, and you can write this as 1 over omega C Rs. So, well, this is for the series, but if you have, for example, a parallel combination like this, I don't have much space, but anyway, so let's fit it in. So let's say we have a reactive element. It could be capacitor, it could be inductor. Let's denote this by X. This is the reactance, and then we have, let's say, a parallel resistance Rp. In that case, in the previous cases, we have the series resistance, which is showing the loss, modeling the loss with the component. In that case, the quality turns out to be the reciprocal of what we have in series. So that is Rp over X. Okay, you can show this. I mean, the way you have to show this is you calculate what is the parallel, you can convert this parallel combination impedance to the series impedance, and then you can take the ratio of the imaginary part of that impedance, that is the reactance, divided by the real part. Okay, and it turns out that the quality factor of the component in when you have a reactor, inductor, or capacitor in parallel with the lossy element Rp, it turns out that the quality factor is Rp over X. Okay, X is the reactance. So the power dissipated in non-ideal component is the power that does not reach the load. So with the lossy components, we must consider a matching network's efficiency. Now it turns out that this lossy lossy elements, inductor or capacitors, they have some loss. Okay, and for example, if you go ahead and connect a load with it, we have a load RL. Not entirely all the energy is dissipated in the load. Okay, I mean you don't have all the for example power being delivered to the load. So I mean the idea is that the same current is going to flow, for example, in a series reactor, and there will be some loss I square RS in this in the series resistor, which is in series with the inductor, okay, which is modeling the loss in the inductor, and then it is in series with the load. So if you have to calculate the efficiency in that case, in this case, in the series case, is defined as power out divided by power in, and the power out, if you can figure out correctly, is the power which is delivered to the load. So this, in that case, is I square RL, and since this I is the series current, so this happens to be the same current that is going to flow in the resistor RS, series resistor RS, lossy series resistor RS, plus I square RL, right? I mean, so this is the total power. Now this can be expressed as 1 over 1 plus RS over RL, right? And if you recall that the quality factor associated with the circuit, if I can, so this is electrical quality factor of the circuit, and for this circuit I can write the quality factor considering that inductor is lossless. Okay, there is no loss associated with inductor. Well, that's equal to XL omega L, okay, at that particular frequency, divided by RL. Okay, so there's no RS. Okay, so if you consider the quality factor of the circuit with the lossless inductor, and then you consider the component or the unloaded quality factor of the inductor, comparing these two and driving a new expression for efficiency, because we have this ratio RS over RL, efficiency can be expressed as 1 over 1 plus Q electrical, because we have R load in the denominator, and then this is the Q unloaded. Okay, this is the Q unloaded. So you can see one way to increase the efficiency is to increase the unloaded or component quality factor. Okay, so you have to have a lossless, I mean if you have a lossless inductor, okay, so the quality is infinity, then the efficiency approaches to 100%, right? You have a large efficiency, and you have a very you can say a narrow band Q, okay, in that case. So if you have a lossy inductor or capacitor, then not entirely all the energy is transferred to the load. There is some loss in the matching network, because the matching network is constituted of LC elements only, whether it is a pi configuration, T configuration, or a simple LC matching network. So normally we can make approximation that the values of LC and the value of associated resistor are constant throughout the band of interest. So over the band of interest means the over the range of frequencies over which you are going to match. For example, this is your matching frequency, and you're going to have, let's say you have a very good match, and the Q is reasonable. So over this band of frequency, we do not assume that this loss RS or series loss or the parallel loss, these resistance values are going to change together with the lumped component values of inductor and capacitors. So let us consider the efficiency of the L network that uses a series inductor and a parallel capacitor. We shall assume, but I mean, there could be other configurations, but series inductor and parallel means you can have a parallel capacitor like this over here if RS is large, and then you can have a series inductor like this. Okay, so this replaces the matching network. This is basically the matching network, and then you can have this with the RL. So we shall assume that the loss in the capacitor is negligible compared to the loss of inductor, and this is the case in the lumped components. The dielectric loss is not much as compared to the loss in the inductors. So we shall model the lossy inductor as an ideal inductor in series with the resistor value RS, just like over here. Okay, so this is the case, and what we're doing over here is the same thing what we have done in the previous slide. So the ratio of the inductive reactance XL to this resistance is the quality factor. Now this subscript U, QU, represents the unloaded Q or the component Q. So less the series resistance RS certainly implies high component quality. So it's a component quality, it's not associated with the load. It has nothing to do with the load. Okay, it's not the circuit quality. It's the quality associated with the component, and that component is the inductor in that particular case. Now, note that this resistance, like the inductor, is in series with the load resistor, so the same current flows through both. So the power delivered to the load is I square RL, and the power dissipated in the series resistance RS is I square RS. So, given the relationship of the circuit Q, this is the circuit Q where you have the load. So XS is the reactance of the inductor at that particular frequency omega L, and QU is the component quality factor associated with the inductor itself. So that is omega L over RS. RS is modeling the loss in the inductor. So efficiency is defined as, again, the output power over input power, and you can express this ratio in terms of the component quality factor and the electrical quality factor. So, you know, one way to maximize this efficiency is by maximizing the ratio QU by QL. That is, if you have to maximize this ratio to maximize the efficiency, then that implies you need to have a very high unloaded Q. I mean, you need to have QU to be high. Okay, this has to increase. So if this increases the efficiency of the matching network increases. Okay, so the only way to increase the efficiency is to have a very high component Qs or lossless LC components in the matching network. So if you have to increase the ratio QU by QL, that is the ratio of the unloaded Q to the loaded Q. Okay, I mean, you cannot do anything for the load. Load is fixed. Load is fixed, and the thing is that the difference in the load and then what you have in the source resistance defines the match Q. For example, you know that in the previous videos what we talked about is that the quality factor of the match can be expressed in terms of R high or R low, R high or R low. And I mean, high could be anything. It could be either the load resistance, or it could be the source resistance. So this is R high or R low minus 1. Okay, if the ratio is high, then you can ignore this 1. But if the ratio is high, you're going to have a very high matching Q, right? But if the ratio is near to unity, then you will be having a very low Q match. That means very wide band match. So to keep this quality factor high and to avoid any damping due to the components, you need to have a very high QU. This quality factor is not defining the efficiency. Okay, this quality factor is defining the efficiency. Okay, so unless you're going to have a near lossless or a very high component Qs, the efficiency of your overall match network is going to be compromised. All right. So if you model the lossy inductor as a parallel RL LR circuit and define the unloaded Q as RP over X, you get the same expression for the efficiency. So the expression of efficiency that we have seen over here is not going to change, even if the circuit configuration is something, I mean, like this. If you're going to model the inductor as, for example, you're modeling the loss as a parallel resistance RP, then you know in a parallel RL circuit, just like in a parallel RL circuit, the quality factor is the inverse of series, what you have in series. So again the component quality factor will be RP over XL, okay, which is again omega L, right, at that particular frequency. And same goes for the capacitor. I mean, this component could be capacitor as well. So this will be RPU into omega C, right? So likewise, if the loss occurs in the capacitor, we'll also get the same expression for the efficiency. Efficiency expression is not going to change. What we have seen over here is going to be intact. Now, as long as we define the unloaded Q of the capacitor again as a parallel resistance over parallel reactance, so it will be parallel resistance over parallel reactance. Or we define this as a series reactance or a series resistance if the combination is in series. So when the efficiency expression stays the same, okay, that's the point. So when the load resistance is very different from the source resistance, the effective Q of an L network will be high. So for high efficiency, the unloaded Q component must be very high, okay. So that's given over here. I mean, if you're going to have the difference, if the ratio is high, I mean the ratio or the difference, the source resistance and the load impedance are different, resistances are different, you're going to have a very high Q match, okay. But that can be compromised if the component quality factor is low, okay. So that can be compromised. So you need to have a very high component Q. So the double L network, for example, has a lower Q, so with its lower loaded Qs, can be used to provide higher efficiencies if the component Q is high, okay. Now the loaded Q, that is the circuit Q, which includes the load as well. The quality factor associated with the circuits can be either high or low depending on the application. Narrowband filters have a very high loaded Q, so they're highly selective filters. Okay, I mean such circuits, for example, they occur in tuned radios receivers. Okay, so whichever station you have to select. Selectivity is defined by how narrowband characteristics or how high Q, how selective or high Q the tuned circuit is, right? So that, but that depends on the application, right? So wideband, for example, on the other hand, the wideband matching circuits have a low loaded Q, and loaded Q is therefore not a measure of the quality. Unloaded Q, however, which specifies the losses in the component, is indeed a measure of the quality, since lowering the component losses always increases the efficiency. So, I mean, this point shows that your expression for the efficiency of a matching network is being determined by this factor, which is the unloaded Q. And you have to increase this unloaded Q in order to get an efficient matching network. Okay. So that's all for the on the efficiency of matching networks.